using these standards only up to the several network or areas. So they are restricted to a particular network or areas or part of the system. Now in 2003, IEEE has taken a step just to commercialize, right, standardize that though any utility or any public or private power producer wish to install any distributed energy resources, which you call DG, then they have to follow or they must follow these standards, right? And these standards are known as IEEE 1547 interconnection standards, and it was given in 2003 by IEEE, of course. Then again amended later on in 2011 and in 2018-19. So that we will discuss later on. So the point is, why? What is the need? Why there is a need to develop these standards? Of course, the objective to develop this standard is the interoperability. That means the some utility in Europe is following some X standard, utility in US is following some Y standard. So there is no interconnection, right? There is no interoperability among all these standards, all these utilities. Maybe manufacturer wise also there is no interoperability and so on. So to achieve this thing, maybe interoperability, long-term stability, and so many other things, they have suggested, means IEEE has introduced these standards. But the question is why there is a need to develop this standard. And the reason is the penetration of renewable energy sources, right? We called distributed generators, but when I say distributed generators, DG, or maybe when I say distributed energy resources, DER, that does not mean that they are always renewable energy sources, RES, right? Renewable energy sources. They can be renewable, they can be non-renewable. So we cannot means sure that okay, whenever I talk about distributed generators or distributed energy resources, they are always renewable. It is not like that, right? The reasons are, just give you the examples. We know that when we talk about distributed generator or distributed energy resources, we are thinking that okay, we have solar based or photovoltaic based generation, and we are going to connect it with our conventional grid. Okay, true, correct. We have, let's say, wind based generations also. Maybe if we have coastal areas, maybe in Saurashtra region or some other regions related in nearby Surat, or maybe we have in Tamil Nadu or the some coastal areas. Then we have these things, right? Means we have wind farms or windmills are there. So of course we do have wind-based power generation. They are also renewables. We have, let's say, photon exchange membrane-based fuel cells are there, which are also acting as a renewable energy sources, because nowadays uh, the smart grid forum that was established by government of India in 2014-15. Similarly, just 2-3 years ago also, the government of India has established another forum, right? This is that was related to hydrogen based transportation or vehicles or fuels, right? So nowadays government is planning to encourage hydrogen based vehicles. The best example that is railways, right? The best example they initiated in from railways. Or maybe I will give you two examples regarding this. The first example is, I hope, I don't know whether you have read the news or not. The Tata has recently developed the fuel cell based bus, right? In collaboration with ISRO. So I think this was the recent news. So this bus they are trying to use maybe in some big cities, metros like that. So this is one news, and the other news is related to the railways.
Hello. Hello. Good morning. Participants, kindly respond.
Yeah.
So I don't know whether you.
Hello. Hello.
So good morning, sir.
Good
Good
morning.
morning.
I think there is issue.
Oh, oh, oh. Oh, how it is disconnected? Internet is working. Okay, okay, okay. Is the screen visible?
No, sir.
Okay, okay. Is it visible now?
Yes, sir. Yes, sir.
So, Naman, please tell me if the connection got disconnected, then please let me know, right? Because I don't know whether it got disconnected or not because I have shared the screen, so I did not get the message. So, from where
Sure.
we
Sure, sir.
now a participant has to tell me from where we are earlier. Yeah, anybody can tell me uh, when it got disconnected,
Uh,
which issue we were discussing.
Sir, we are discussing about fuel cell in railway.
Yeah, yeah, okay, good. So, uh, did I talk about the fuel cell used in railways? Yes. Did I talk about this?
No, sir.
Okay. So, as you know, fuel cell is also now government Ministry of Railways is encouraging the use of fuel cell. And I don't know whether you are familiar with the northern side. I don't know whether you have visited or not. But there is a place near Chandigarh known as Kalka. And another place is in Himachal, that is Simla. I don't know. Are you aware of this? Yeah. Yes. Are you aware of this? Am I audible or not?
Yes, sir.
Yeah. Okay. So there is a train running between Kalka and Simla. It's a very good train, toy train, known as Himalayan train or Himalayan Queen. I don't know. And it took around roughly around maybe 7 hours to reach from Kalka to Simla, but it's a really good train, right? You have to At least if you have not visited, you can take this train and with your family, maybe kids are really enjoying this. Now the thing is that this train is uh, running by diesel locomotive. So I don't know in Gujarat or also earlier I know between the Anand and Khambat, I think the diesel locomotives are running, and Damu, which you called. So nowadays I don't know whether it is running or continuing or not, or maybe it may be electrified also. So here the reason is the pollution, because when you use diesel locomotive, the pollutions are really very high, right? And we have greenhouse gases, CO2, SO2, carbon monoxide, as sulfur oxide, or water vapor. Five gases are there which are known as greenhouse gases. So to avoid this, the Ministry of Railways has given the project to convert this diesel locomotive into hydrogen based fuel cell with battery, right? And I knew this because the project was given to me. So our task is to, because when you use the train in hilly areas, then train needs power, and this power is known as tractive effort, right? So tractive effort required by the train, maybe when the train is starting or maybe train is running, right? Basically, when train starts, it requires more tractive effort or power. So tractive effort required by train in hilly areas, that is higher compared to the tractive effort required by train in plain areas. Right? That is true, understood. So because of this reason, there is a it is really a difficult, because we have a space of locomotive that is fixed, right? Space of locomotive that is fixed. We know, you are also know the first locomotive or engine, where the engine is there, motors are there. Earlier they were using DC series motor, then it was replaced with induction motor, right? So where the engine is there, motor is there, other things are there. So there, that space is limited, and everything you need to accommodate. If I convert diesel locomotive into this hydrogen based fuel cell with battery, everything I need to accommodate in that. So I have a space constraints. I have a attractive power effort, means I need some power. Train needs some power so that it can start at a continuous speed. So that effort is required. And the third thing is that when you are in hilly areas, you have some other constraints are also there, like some aerodynamic constraints are there, some other constraints are there. So those things are also there. If fuel cell sufficient hydrogen is not there, because fuel cell, it converts energy in one stage, right? Basically it's a converts the energy, chemical energy, into electrical energy. So this is one stage conversion, compared to our conventional power station, which works in two stage conversion, right? Early what we are doing, we are, let's say, conventional fuel, fossil fuel based power plant. We are generating steam, and steam is going to run your turbine. So one stage conversion. So then the steam is converted into turbine mechanical energy, and then turbine is coupled with the shaft of the generator. So mechanical energy is converted into electrical. So two stage conversion. So that's why efficiency is less for these thermal power plants, maybe 30, at the most 40%, or if you use combined cycle, 45%, and so on. But here in fuel cell, the energy efficiency is 60%, right? So the reason is it works in a single stage conversion. But when I use fuel cell, means hydrogen is used, right? So that you can convert that energy into electricity, and you will get water as a byproduct. But the point is, how do I refilling? Means how the refilling of this hydrogen is done, because we do not have hydrogen refilling stations, right? So refilling is very difficult. So that arrangement also we need to see. So when I talk about hydrogen based power plant, then all these constraints we need to consider, and then we need to give the design, and then that design is used by some industry to develop the prototype, and then testing of prototype is there. So maybe it will take 3 years almost, right? To convert this diesel locomotive into the hydrogen based or maybe battery based locomotive, and that is user means that is environment friendly, right? Because that is what we need. So this is the reason why government is encouraging, or Ministry of Railways or Ministry of Transports, they are encouraging hydrogen based fuel cell in transportation area, because they want clean transportation, right? So the reason is, when we penetrate distributed generators or distributed energy resources into the grid, this is the main thing which we need to consider, right? And when we the question is, not only we have renewables, we have non-renewable sources are also there, which we can treat as a DG or distributed generators or distributed energy resources. Let's say we have a CHP, combined heat and power plant, right? CHP type of power. So this are nothing but the non-renewable energy sources, but we can treat as a DG, right? So all these things are there, which we need to consider when we talk about the penetration of distributed generators into our conventional grid. So the reason why the interconnection standards IEEE 1547 is required, the reason is because of the penetration of renewable energy sources as well as non-renewable energy sources, which we are treating as a DG, distributed generator. It can be, let's say, micro turbine. It can be, let's say, we have induction generator based wind power plant, or permanent magnet synchronous generator based wind power plant. It can be anything, right? Solar based, anything. So whatever biomass is also now government is encouraging. So DG can be anything. It can be renewable, it can be non-renewable, but 90% cases it is renewable, right? Because of the clean power and environment friendly nature. So this is all about why there is a need to develop IEEE 1547 interconnection standards, and the main reason is the penetration of the distributed generators into the grid, and there is no standard existing. So that's why to achieve the interoperability among the all the different standards which were available earlier in different regions, there is a need to develop some standards, and that's why interconnection standards was given by IEEE. So I hope this is clear, right? Am I audible now?
Yes,
Yeah,
sir.
yes, sir.
Yes, sir.
Okay, thank you. So now when we integrate, that means when the interconnection of distributed generators are done in our conventional grid, it can be maybe at distribution level interconnection is there, maybe we have sub transmission level interconnection is there, we have transmission level also interconnection that can be carried out. It depends on application and the size of the DG and so on. So many other parameters are there. Now the question is, when such integration is there, what are the issues that is faced by during integration, right? So I have listed several issues. Maybe these are not all issues. Few issues are I have listed. So the first issue is related to the MPPT control of PV system. That means if you use solar-based power plant, then how to control the maximum power point tracking of solar system, that is also a tedious and complex procedure. Same thing is also applicable for wind system, because there also we need to track the maximum power from the wind, right? So though I have mentioned only for solar, but it is applicable to wind also, right? So the point is how we are going to track the maximum power from the solar or wind. That is also one big challenge, right? Of course, they are using some maximum power point tracking algorithms based on maybe pattern and observe method, and maybe some other methods are there, right? But anyway, we are not interested in that. So this is, but of course, whenever we use some methods, each method has its own advantages and disadvantages, right? Basically, the main thing issue is the how much sensor we need, because when I say I need to track the power, that means power is a combination of voltage and current, uh, right? If I talk about PV, because the power generated is DC in nature, so I need voltage and current, so I need two sensors, voltage sensor and a current sensor, so that I can track the voltage and current continuously, and then I have the power value. So of course there are some issues in that. The second issue that is related to the power quality, right? So we know that the total harmonic distortion is a term that is associated with power quality, but there are of course several other terms are also there, like voltage sag, voltage swell. We have the transients, momentary transients, interruptions are there, voltage dip is there, voltage flicker is there, waveform distortion is there, harmonics are there, interharmonics are there, the noise that is also there. So many things are there which are related to high power quality issues. And of course, the several IEEE standards are also available for power quality issues. The main standard is IEEE 519 standards, right? And then again, some other standards are also there. But anyway, we are not interested in that. So when the power quality issues also are also there, because whenever what is the reason why power quality issues are there? The reason is the type of the generator which we are using in DG. Let's say if I consider solar based generation, and I have to use inverter, right? Because whatever power is generated by solar, that is DC, and we need inverter so that it can be converted into the AC, and that is again synchronized or with the grid when you give it to the grid. So because of this, obviously, the when we have inverters, maybe you can use MOSFET or IGBTs as a switch, and of course, you have some driver circuit is also there. So for that, you have to control the duty cycle, and you know, right, very well the working of inverters. So in that case, obviously, when you switching will take place, the harmonics are generated and the quality of power may deteriorate. So power quality issues are also there. The third issues are related to integration issues. So integration issues, you have studied at undergraduate level. If I wish to integrate any uh, any generator, right? I hope you have performed experiment in electrical machines also, that if I wish to integrate one generator with the another generator, then we have to follow voltage, frequency, and phase sequence should be same, right? I hope this you have studied. Have you studied this?
Yes, sir.
Yeah. So you know, right?
Yes, sir.
So similarly, when you integrate your distributed generators with conventional grid, right? Obviously, you have to integrate at some point, and that point is known as PCC, point of common coupling. So when you integrate your distributed generators any kind with your conventional grid, maybe at distribution level or maybe at sub transmission level or maybe at transmission level, then certain integration issues are also there, right? Voltage should be same, or delta V at the most. Change in voltage should be same, change in frequency should be same, phase sequence should be same. We are talking about integration with AC system, not DC system. So this all these issues are there. Of course, we have some other issues are also there in integration. So if fault is there, whether I have to integrate or not, so many things, right? So integration issues are also there, which we need to consider. The fourth issue that is related to islanding, right? So we will see what is islanding, how practically we can talk about islanding. That we will see with some case study. And islanding, what is islanding? Just give you one in one word. Islanding is nothing but it is similar to island where we are going for a fun, right? No, we are going to beach, or maybe we are going to some island like Lakshadweep or Andaman Nicobar. These are the islands in and where we are going, right, with our family for fun. So similarly, island is nothing in electrical island we are talking about. So an electrical island is nothing but a phenomena in which a small portion of the power system network is disconnected from the grid, and in that small portion of the network, you have local distributed generators which you have installed, and depending upon its capacity, it is going to give the power to the local loads that is available in that small island, right? That is nothing but electrical island. But of course, island is always means not required, it is hazardous. So that's why islanding has certain disadvantages also, we will discuss, right? The next issue is the change in coordination philosophy. So we know that when we do not have any distributed generators, right, then our system, distribution system, if I talk about, uh, you are well aware of the distribution network in our country, right? That is, we have primary distribution network and secondary distribution network in our country. So primary distribution network works at 11 kV, and secondary distribution network works at 415 volt three phase. It is three phase four wire system with neutral, and of course we have the domestic or residential consumers, that is single phase 230 volt 50 hertz system, right? So two types of distribution systems are existing in our country, primary and secondary. So in this, when no DG is there, if we do not connect any DG, then this distribution system is radial in nature, right? We have source from one side or left hand side, we have load on another side or right hand side, and then you can easily, because if you have radial system, there are many advantages. It's a very simple system, right? There is no complexity involved in that. You have source from one side and load connected on another side. So even the protection is very simple. You can use simple overcurrent relays or fuse, right? At 415 volt, we are utilizing HRC type of fuse, high rupturing capacity type of fuse, or maybe at 11 kV you can use dropout type of fuse, or maybe you can use relays, overcurrent relays, simple overcurrent relay, fine, right? But as soon as you connect DG, right, at different location, we do not know at what location we connect. It depends on the supplier, right, who is supplying, and the customer who is producing or installing DG. So location, that is not in our hand. Size, that is also not in our hand, right? The thing is that as and when I connect DG, my radial structure, that is not there, right? This type of radial structure no longer exists as soon as I connect DG into the distribution network, right? Because now you see the power is available from both the sides. Let's say near load I connected three DGs, right? Each having capacity of, let's say, 1 megawatt, right? So then the power is available from left side, we have grid source, right side we have DGs. So it is not the only power is not in one direction, It flows in both the direction. So bidirectional power flows are there. So then you have a coordination issues between the relay, between the fuse, between the recloser. Recloser is again the device which is used by most of the utilities in our country also. We have installed reclosers, not at distribution level but at transmission level, right? Just to improve the service continuity and reliability. So I hope you aware whenever means I am talking about this are installed in our country at 132 kV transmission line or 220 kV line or maybe 400 kV line like that. So the function of recloser is whenever fault occurs, we know that the circuit breaker becomes open, right? The three pole of circuit breaker becomes open. After some time, it will reclose automatically. That is the function of recloser. So if transient fault is there, it die out, right? We know that 80% faults are transient in nature. So it will die out automatically. So if I reclose after some time, there is some standards for that also, right? So 0.3 second is the waiting time period. So after 300 millisecond, if I reclose the circuit breaker and if fault is not there, my system is healthy. There is no need to send the lineman for maintenance and so on, right? There is no manual closing of circuit breaker is required. Nothing is required. But when you connect DG with this system, such type of system, any whether distribution or transmission level, then the coordination becomes very difficult, right? Because of the bidirectional power flow from any direction, right? Either both the directions or multiple DGs are also there. The next issue is related to voltage regulation and losses. We know that at distribution level, voltage regulation plays an important role, right? And that is the fundamental difference, that if I have distribution network, the percentage voltage regulation should remain within plus or minus 5%. Whereas if I am calculating voltage regulation at transmission level, then I think the it may exceed 10% also, right? There is no harm in that, because at transmission level efficiency is more important, right? Losses should be as low as possible so that power available at sending end and power to be transmitted and available at receiving end, the ratio of that, which is efficiency, that should be as high as possible, right? So that there should not be any transmission losses. That should not be, or if it is there, then these losses are minimum. So voltage regulation play an important role at distribution level, right? Even losses are also now equally important at distribution level because of the demand side management and some other issues which we are handling by the utility. So voltage regulation, when you connect DG with the grid at different locations, there is a change in voltage regulation. Basically it increases and it may violate your distribution limit plus or minus 5%. So then you need to do something so that it again comes within the prescribed limit, right? Losses are also going to increase, okay, when you connect DG. So if losses are increasing, then again efficiency at distribution level also reduces. So then you need to think about this also, right? Is that clear, this thing?
Yes, sir.
Yes,
Yeah,
sir.
yeah. So that is there. Fine. So the next issue is the effect of harmonics, right? So as I have already told you that we have power quality issues when the penetration of renewable energy sources or DG in the form of DG is there. So yeah, harmonics are also there. And and there are several impacts of harmonics. You know, the harmony, because of harmonics, there are many impacts are there. Maybe if you have induction motor working as a load, then torque is going to reduce, and there are many effects, right? Impacts of harmony. Even your the neutral current in the neutral conductor also increases because when I design the neutral conductor in three-phase four-wire system at 415 volt, then the cross-sectional area of neutral conductor I considered half of the phase conductors. But because of this harmonics and deterioration of quality, power quality, the current in the neutral conductor exceeds. So now the practice is that the cross-sectional area of neutral conductor should be same as phase conductor, right? So cost increases, then cost increases because of this. So of course there are some other impacts also. That is also there. Okay. Then the increase, and if you have harmonics also, then you can see that the waveform distortions are there. Say the best example is in our house, we are using many smart appliances, right? Let's say we are using laptop at present where the lecture is going on. If I just take if I connect the laptop and if I just see the voltage and current waveform in our house, it is no longer sinusoidal in nature, right? You can try, because I have captured. So it is, you won't find that it is sinusoidal in nature, right? We are using, let's say, a microwave in our house. Maybe you are using the electronic fan regulator, right? Instead of earlier rheostatic regulator, we have a small knob type regulators are there, right? So again, all these are the source of production of harmonics, right? We have, let's say, washing machine, we have smart devices, right, supported by Alexa or Bixby. So all these are the production of the sources of harmonics. So this is also there, right? The next issue is the increase of short circuit level. When you connect DG, let's say DG is not connected, then obviously at a particular bus, if you measure fault MVA, I don't know whether you have done at UG level, you have studied the fault calculations, right? So there you have calculated the fault analysis. You have done the fault analysis and then you have obtained the fault MVA at particular bus. And that MVA is responsible for deciding the capacity of circuit breakers. So circuit breaker capacity is defined basically by two ways. Of course, there are some other specifications also, but mainly breaking capacity and making capacity of circuit breakers, right? Switch gears. Breaking capacity and making capacity of circuit breakers. Making capacity is always higher than breaking capacity of, that is also there. So this short circuit level or fault MVA, that is associated with the breaking capacity of circuit breaker, right? Now if I connect distributed generators into the grid, let's say I have connected multiple DGs into the grid at different location, and let's say I have connected the total DG 10 DGs, each of let's say 5 megawatts, or total 50 megawatt. So obviously this is going to increase the short circuit level, and if short circuit level increases, then the breaking capacity of circuit breaker I need to change, right? Because then the circuit breaker is not capable to withstand that much fault MVA. So the only option is I have to change the circuit breaker. Circuit breaker is a very costly device. If I just give you the cost estimate for 11 kV circuit breaker, because normally at 11 kV in most of the substations in our country we use vacuum circuit breaker. I hope you heard this name. So the cost of ABB make vacuum circuit breaker, that is roughly around let's say 25 lakhs. That is roughly around 25 lakhs. Maybe 1 year back, I don't know, after COVID, what will happen to that cost. So this is for this one circuit breaker, right, which is capable to take care of the three conductors RYB, one feeder which has three conductors. If I have, let's say, 11 feeders in substation, then I need 11 circuit breakers. If fault MVA or short circuit level increases because of the penetration of DGs, then I have to replace all circuit breakers, because otherwise they are not capable to withstand that much fault power, right? Fault MVA. So this is also the major issues, right? And nowadays anyway utilities are doing retrofitting. How they are doing, that is different issue, but they are now doing this thing, that as a part of solution of this. And so this is also the one of the issue which you need to consider, right? The next issue is the grounding and transformer interference. See, when no DG is connected, your system, right, that means a utility or distribution substation, some type of grounding is there, transformer is also there, right? Maybe you have delta delta or delta or star star transformer is there. Okay. Now, as and when you connect DG, grounding plays an important role, right? Grounding, that plays an important role. What type of grounding you have done? Because depending upon whether your generator is delta connected or star connected, accordingly you have done the grounding. So whether you have done the resistive grounding or effective grounding or non-effective grounding, this all these things are important. Maybe you have the some other type of grounding is also there. So that is going to play an important role, because when you connect the DG with the grid, because grounding, just give you simple example, if I have a grounding, if I have done the grounding, then the zero sequence current, if I am doing some measurement based on zero sequence current, and if I am using delta connection, then you know that zero sequence current, they are not going to they do not come out of this delta winding, they remain circulated in delta winding, right? So grounding plays an important role. So I think is this clear, all these issues? Yes.
Yes, sir.
Yes, sir.
Okay, fine. So now I think I am only at slide number 3. Okay, so now let us proceed further. So I am moving at next slide. I hope it is visible. So this is related to the connection of DG to the grid. So you can connect the DG at any level, as I told you, right? So maybe you can connect DG at low voltage distribution level. The examples are, you have individual photovoltaic panels based power generation. Maybe you can have the microchip. Okay, you can have the microchip, or maybe combined heat and power CHP type of systems or generators that you can connect. You can also connect at 11 kV to 66 kV, that is medium voltage distribution grid. In our case, we have only distribution grid up to 11 kV. After anything above that, we are treating as the sub-transmission level, because after above 11 kV, we have 33 kV and 66 kV. But nowadays 33 kV is not there, means the utility is removing this thing. So we have, after 11 kV, we have immediately 66 kV, right? And that is sub-transmission. So small scale hydropower plants, you can connect. Biomass based systems, you can connect. Tidal and wave systems, that also you can connect. And this small industrial combined heat and power plant, this CHP, small industrial CHP type of power plant is very common in development, some US and Canada and UK countries, because they are utilizing this in every home, right? Just because they have a centralized heating system. So for that, this will be very useful. So small scale hydro, biomass, tidal, wave, small industrial, all are nothing but the example of distributed generators, which you can connect, or whether say interconnect with the grid at 11 kV or maybe at 66 kV, right? Or in between. You can connect this DG at high voltage distribution grid between 66 to 132 kV. And the examples are large industrial combined heat and power type generators, large scale hydro, or offshore wind parks. Right. So nowadays, the offshore wind parks are offshore and onshore wind based generations are very common. Right. And there are several countries, you see Norway, Denmark, Sweden, they have such type of arrangements, even including Germany also, that is offshore wind and onshore wind parks. And even in Norway, I knew there is a one company known as Sintif Energy. Right, there is a company in Norway that is known as Sintif Energy. So this company is manufacturing the wind, means they have installed the wind base generation, or right, in the not the near the bank of the sea, but just slightly inside the sea, that is not onshore. So in that they have combined both solar and wind both. They have combined solar and wind both. So this is the only company which is providing both solar and wind in a single unit. Right, so you have a solar and you have the wind also, and there are reasons why the company is has given this arrangement, because solar, that does not work during night time, right? And the wind, that is not, I don't know, maybe sometimes when sufficient wind is not there, then you have to depend on solar. So it's a combination of hybrid solar wind type of generation is there, right? So that is what this company is giving. And so anyway, this is just for knowledge. So we have transmission grid also. You can connect DG at maybe higher one, greater than 132 kV also. And in this case, the examples are very large wind parks or solar parks. Let's say the best example is in Gujarat, Chanasma near Patan. We have a very big power plant like solar. So similarly, we have wind parks also in Tamil Nadu, in several regions. We have the wind parks, large wind parks. So they are connected at transmission, directly at transmission grid. Right? Is that clear, this thing?
Yes, sir.
Yes.
Sir, yes, sir. Yes. Please.
Okay. So, okay. So now let us go to the next slide. So as I told you, the IEEE 1547 standards are there. So just I wish to give you, this slide will give you the overview of the standards, right? So as I told you, this standards is known as series of interconnection standards. The name of the standard is series of interconnection standards, and it is an interconnection. It is a standard related to the interconnection system and interconnection test requirements. So basically, it is a standard which tells you everything about when you connect any distributed generators or distributed resources to your conventional grid, maybe at distribution or transmission or any other level, right? So now what is there inside this standard? So in 1547.1, the means point 1, they have given the, you can say, first chapter, you can consider, they have mentioned the interconnection test procedures, right? What are the tests to be carried out when you do the interconnection? So all these things are mentioned in point 1. In 1547.2, the guide, the complete guide of this standards is mentioned. In 1547.3, the information related to exchange between the distributed generators and utility, that is mentioned. So suppose you have installed 3 DGs and you have a grid. So now how the exchange will take place, exchange of data, exchange of information will take place between all these DGs and the utility. So what type of If you use some communication medium, then what is the minimum rate, bandwidth, everything that is mentioned in 1547.3 guide. And in 1547, the information related to island or island systems, that is given. So this four things, 1547.1 to 4, this basically this are the different chapters, you can say, that is given in this interconnection standards. So I hope that is clear, right? Is that clear, this thing?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, fine. So now let us move ahead further. So if I just consider these standards, right? What are the general requirements of these standards? So voltage regulations, grounding, synchronization, right? Of course, voltage, frequency, phase sequence. Isolation devices, means what type of isolation devices. If I wish to open the DG, or if I wish to disconnect the DG from the grid, then what type of device I need. That this device are known as isolation devices, right? And of course, some other things are also there. Inadvertent energizing means something goes wrong and you are trying to energize multiple times, then what happens? So let us move further. So I have changed the slide. And of course, there are some other issues are also there, like voltage, frequency, loss of synchronism, faults, right? All these things are there. But anyway, we are not concerned about this. So now let us see what is islanding, right? So as I told you that islanding is nothing but the situation in which the system is electrically isolated from other parts of the system, but still continues to be supplied by other sources of generation. What is the meaning of this? So let us consider this. I hope this is visible, right? This figure, slide number 9.
Yes, sir.
Yes, sir.
Yeah. So here you can see I have the grid at one side, left hand side. Then this generator or utility grid is connected with some transformer. Okay. And then we have one bus available, and then we have several feeders. So here I have mentioned two feeders, feeder 1 and feeder 2. But you have again n number of feeders are there emanating from this bus. Okay. If I consider feeder number 1, then you can see this is a feeder, and this feeder, if I just give you the example, let's say these are the HT consumers, 11 kV feeders are there. Let's say feeder 1 is 11 kV, feeder 2 is 11 kV, and so on. So here I have taken, you can see the cursor, here I have taken some tappings, right? And then load I have shown. So this is nothing but laterals. These are known as laterals, right? So any tappings which you take from the 11 kV feeder, right? Then those are known as the laterals in distribution network term. So you can see these feeders are again connecting with another bus, okay, where you have a local load, both the sides, and then you have a DG I have connected here. And between these two, right, that means DG, which is coming, and on feeder 1, there is another device also. I put one circuit breaker. Now, let's say something goes wrong, right? Something happens here, somewhere here in this area on the left-hand side of this circuit breaker, right? Anything happens on left-hand side of this circuit breaker, let's say some fault or something. So this circuit breaker becomes open, right? I assume this is a switch, it becomes open. So now what happens? This yellow color, oval shape, right? This type of shape is going to form, which is known as islanded network. Why islanded? Because these local loads are supplied by this DG, right? So this load, of course, it depends on the capacity of DG and what is the requirement of load. Let's say these loads requires a power of, let's say, 1 megawatt, and the size of DG is also 1 megawatt, fine, no issue, right? But if the size of DG is 0.5 megawatt and this are the 1 megawatt requirement of load is 1 megawatt, then this DG can give only 0.5 megawatt. So other 0.5 megawatt load you have to shed it. Load shedding needs to be done, right? But depending on priority type of load shedding that can be carried out. Of course, that comes under again the load shedding, so we are not concerned about that. Okay, so now the question is, if I think this is clear, right? What is islanding? I hope that is clear.
Yes, sir.
Okay.
Yes, sir.
Okay. If I just give you, then again I have changed the slide number 10. If I just give you the larger network view, you can see I have shown anyway. This is a 66 kV bus. Then you have a substation. You have a transformer 66 by 11 kV bus, and many feeders are there from this bus. And one of the feeder I have taken, and you have this laterals, and on this feeders I have connected one DG. Another laterals I have connected another DG, and you can see if I open this R4, right, if something goes wrong somewhere here, and if this R4 is from isolation device, if it is open circuited, then there is a formation of an island. You can see shown by black line, right? Black thick line. So there is a formation of an island, and whatever loads are here, that is supplied by this DG1 depending upon its capacity. So this is also another example of islanding. Now the question is, islanding, how many different types of islanding is possible? So islanding can be of two types. One is intentional islanding and another is unintentional islanding, right? So intentional islanding is done for stability improvement. Intentional means something you are doing intentional, right? Because of some reason you are doing it. And unintentional means you are not you do not wish to do that, but you have to do, right, where something goes wrong, right? So unintentional islanding is done for reliability improvement. So there is a big difference in intentional islanding and unintentional islanding. See, such type of classification does not exist. This I have made, right? The reason is, the intentional islanding is done in most of the developed countries. It is not going to happen in our countries, right? I will tell you the reason later on. The intentional islanding, which is done for reliability improvement, that is going to happen in our country, right? So there is a fundamental difference between the intentional islanding and unintentional islanding. That's why I made this classification, right? That is the only reason. Is that clear, this thing?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay, fine. So now let us proceed further, right? So let us see first what is the intentional islanding, right? Oh, sorry. I think yeah. What is the intentional islanding? So as I told you that intentional islanding is done for stability improvement. It is done for stability improvement. So that means your network is there. Maybe several DGs are connected with your network, and intentionally you are creating islanding, right? Why? Because the stability improvement. Stability improvement means stability is related with what parameter? Voltage. If you observe that in some of the regions voltage collapse are there, right? Suddenly voltage reduces drastically, and and this voltages are reducing below certain prescribed limit, let's say 0.85 per unit, then you are doing some intentional islanding so that your voltage collapse stops, and again the original voltage that is regained at most of the buses. Is that clear, this thing?
Yes, sir.
Yes, sir.
Yeah. Now let us see just one case study, right? That how intentional islanding is to be carried out. So to understand this, what they have done, they created one test setup in the laboratory. So modeling is carried out because you need some data, some network, right? From where do we get the network? So they have taken European grid network. European grid network is a very large distribution sub-transmission network. It contains several buses, more than 1,000 buses, almost 200 generators and so on, right? I will show you the details. Then what they have done, they have developed a logic, means some algorithm, right? Some program for controlled islanding. How the control islanding done, what parameters you need to know, you need to monitor, based on that what decision you need to take, that are coming under the algorithm of control islanding. And then how you can prevent the blackout if you adopt or if you go for controlled islanding, and then demo that is also there. So let us see what is the laboratory setup. So this is the laboratory setup which is there where I worked. This is at the Texas A&M University, USA. So this setup is developed by me along with the few research scholars. So that's why the name is given TAMU Synchrophaser Test Bed. TAMU is the name of the university, Texas A&M University, right? Short name, acronyms. So here what we have done. So we have considered here the European grid network, right? So we have taken the data, the entire data is available with us, and this European grid network, the total number of buses are 1354. So it is a 1354 bus European grid network we have considered. We carried out the modeling, right? And modeling is done in one software which is known as RT-Lab software, Now, if I just do the modeling, then there is no means how could I validate this modeling? Means whatever modeling I have done, you are doing some modeling in Simulink of MATLAB or maybe some other software, but how do you validate, right? Whatever you have done, how do you confirm that is correct? Whatever parameters you have selected, those are correct. Whatever waveform you are getting, those are correct, right? We do not know. So to validate this, we have done hardware in loop simulations. So what we have done, this RT-Lab software, we have connected with one simulator, right? Real-time simulator, and this simulator is known as Opel RT simulator. So Opel RT is a one hardware in loop simulator type device. You see the height of this device is almost 10 feet, right? And so height, and the size of this rack, if you see the width on this side, it is almost let's say roughly around 4 feet. So whatever the modeling we have done in this software, this we have acquired, means we have just dumped, right, through this Opel RT simulator. And then we kept some devices, right? These devices are the phasor measurement unit, PMU devices, right? It is known as phasor measurement unit. These are the PMUs, are the nothing but the devices which is used for monitoring purpose. If you wish to monitor the state of the system or grid, you can use the PMU. PMU is nothing but a device which gives you phasor values based on several acquired data of voltage, current. So input of PMU, That is 3 voltage, 3 current, instantaneous values. And the output of PMU, that is RMS value, phasor value, and that is phasor value of voltage, phasor value of current. It can also give you power, it can also give you frequency, it can also give you rate of change of frequency, df by dt, right? So PMU is a device, even in our country also, there is a plan to install several PMUs, right? Until now, I think close to 1,000 PMUs have already been installed by the utilities in our country. So that is not the issue. Okay. So we have installed several PMUs. Am I audible?
Yes, sir.
Yes,
Yes,
sir.
sir.
Fine. So what we have done, the output of this Opel RT simulator, we have passed through the PMUs. And when we have PMUs, the PMU does not have storage capability, right? It is not possible to store any data by the PMU. So PMU will give data to some other device which is known as PDC. It is phasor data concentrator, right? So we have a PDC with some server also, and that PDC, here we have considered open PDC, right? There is no closed loop. Otherwise, normally the PDC can, here the all the data are given to PDC, but there is no reverse. PDC cannot give data to PMU, but in actual PDC we have this capability. Bidirectional power flow is possible, right? And then we have some wall display where we can display the devices. So let us see how we have done this. So what we have done, you can see something here, right? So this whatever you can see on the wall, there is some green color dots you can see. These green color dots are PMUs, right? So we have installed 40 PMUs. You can see this rhombus, right? Basically not rectangle, rhombus. So jisko Sakarpara in Gujarati you call, right? So this type of dot, these are all our PMUs. And if you zoom this area, you can see few lines. These lines are nothing but the European grid, which contains 1354 buses, 260 generators, 1991 lines, and 40 PMUs. That is green one, right? And the whole network we have divided in 4 areas: area 1, area 2, area 3, area 4. This is our demarcation, right? They have not done anything. There are few lines which are connecting between the two areas. Let's say between area 1 and area 2, you can see this red color line. This is nothing but tie lines, similar to the lines which is connected between Gujarat and MP, or maybe MP and Chhattisgarh, like that. Interstate transmission line, right, which you call tie line. So this is similar to tie line. So you have several lines connected between two areas, and the red color indicates the overloading of this, right? Something, the blue color indicates the overloading, red color indicates the outage of this line. Because of overloading, something happens, so that line that is tripped, that line is not available, that line is not capable to transfer the power, right? That is the meaning of red color. So something goes wrong because we do not know what will happen. So then you can see we have not done anything intentional islanding, we have not done. And because of some tripping of the line, as I told you, something happened in these areas between area 1 and area 2. So we have monitored the voltage profile of area 1, area 2, area 3, and area 4, right? So you can see I have shown the voltage profile in per unit on y-axis against time. Then you can see I have shown some circles. Okay, you see the voltage suddenly collapses in area, particularly in area 2. You can see it comes out to be roughly around 0.2 per unit, which is against the standards, right? It should not go below 0.8 per unit or 0.85 per unit, like that. But in all the 4 areas, these voltages are collapsing, right? You can see even in area 4 also. So if this is not acceptable, and then if I wish to avoid this, then I have to go for controlled islanding, intentional islanding, because if I do not take any action, right, because then voltage is RC reducing in all the areas, so voltage collapses, and then finally what happened, it is going to impact the stability of the network, and the big blackout is possible, right? So to avoid that, we need to do some islanding, we need to open, we need to disconnect some feature, right? It is similar to I don't know whether you read something or not. एक कहावत, just like some proverb is there, because when there is a fire in the forest, what you have to do, few trees you have to remove from that portion, so that fire is not going to continue in other areas, right? So this is similar to that. So to protect or to avoid the complete blackout or maybe partial blackout, what you have to do is you have to disconnect the few regions or few lines, and that procedure is known as controlled islanding or intentional islanding procedure. Clear? Is that clear, this thing?
Yes, sir.
Yes, sir. Yes, sir.
Yeah, fine. Okay, fine. So here what you do is, what you have to do is, we used some algorithm, we developed some algorithm, and the name of that algorithm given is known as blackout prevention algorithm, right? Blackout prevention algorithm. So we have identified some areas. The task of this blackout prevention algorithm is to identify some area, right? If I remove that area, then the chances of blackout that will be reduced. So that prevention algorithm, that contains few things, right? Few blocks. So it requires some input. So input are given in terms of several indices. Let's say observability indices and vulnerability indices are there. These indices you can, means anyone can calculate based on some data which you have or which you acquired, right? And then islanding prediction algorithm is there, which is going to predict whether the islanding is there or not. Then you have to trigger control islanding part or some logic, and that is because of that, that is going to remove some lines, that is going to remove some of the lines, or maybe one, two, or some lines, so that the other areas are not impacted, right? So that is the main objective of this blackout prevention algorithm. So what we have done, so to understand this, we have considered, to verify this concept, we have considered IEEE 118 bus system. You can see here in the screen, I have shown here, and this is different than the European grade, right, which has 1358 bus. This is only very small, 10% of that, only 118 bus, 10% of 1358, just to verify the concept. So what we have done, we have considered two areas, right? You can see this dotted line, and you see that we created the island, and you can see in the table the results, that the number of islands we have created, that is two, in area one, in means in this area one island, in this area another island. And then we have the group of generators associated with island. So when island is carried out in, then which number of generators are associated with that. And load shed without control islanding means, if I do not adopt this blackout prevention algorithm, then you have to remove this much of load, megawatt of load. But if we go for control islanding, that means if I use this scheme, if I trip maybe one or two lines, then the load shed is requirement, then we have to remove the load that is of the order of 70 megawatt. Earlier you have to remove the load of the order of close to 4000 plus megawatt, right? So this is the advantage of this such type of intentional or controlled islanding algorithm, right? And I think more details you can find in this paper. It is a SIGRE committee report, and I am the author. Along with this, the other two authors are also there. So you can refer this report, SIGRE committee report, which is presented in Norway in 2019. So you can find more details about this control islanding that is mentioned there. Okay, is that clear, this thing?
Yes, sir.
Okay, and if you just observe the voltage profile of all
Yes,
the
sir.
four areas, you see here I have shown the voltage profile of all the four areas. So here you can see the limit on y-axis, right? I have shown the limit up to 0.7 per unit, 0.6 per unit, 0.8 per unit. So voltage will remain within 0.7 or 0.8 per unit, right? So this is also the another advantage, that why stability improvement is there or why stability is maintained, because the voltage profile of the particular all the four areas, that is going to remain within certain limit, right? So this is also the another advantage uh, for this, right? Okay, so now if just we move further, anyway this demo is not required, I think. So any is that clear up to this?
Yes,
Yes,
sir.
sir.
Okay, okay,
Yes, sir.
okay, fine. So the next is when islanding occurs. So when there is a opening of the breaker, which is known as the upstream breaker, right? Maybe opening of fuse, or maybe opening of some sectionalizing switch, then islanding occurs. Or maybe when manual switching is there, right, by the person who is working in substation, if manual switching is done by that person, then also the islanding occurs. So there are two possibilities in which islanding occurs. Now let us see why islanding is not preferred, right? Why it is not preferred. There are three main reasons why islanding is not preferred. The first reason is the island is an unregulated power system. We know that island is the small portion of electrical power system network which is supplied by the DG to the local loads. Earlier, without islanding, that portion is connected with your grid. So the voltage and frequency that is controlled by the grid, right? Frequency close to 50 hertz, voltage close to 1 per unit, and so on. As soon as islanding occurs and the island is formed, then the small portion in which DG is supplying the power to the local loads, there is no control of voltage and frequency, right? The voltage and frequency control is possible only and only when the DG where you have installed, means the location where you have installed the DG, it has voltage and frequency control features. But normally, because that is very costly, right? Installing voltage and frequency control, automatic voltage regulators for voltage and for frequency control, some other mechanism, that is very costly. So normally when we installed the DG distributed generator at a particular location, they do not have voltage and frequency control feature. So if they do not have, then there is no control on the voltage and frequency. And if there is no control of voltage and frequency, then you see the region in which island is formed, and the loads are already there, right? That is supplied by the DG. So local loads, they may have some equipment, and those equipment have certain limits in under which or within which the equipment operate safely, because they have some frequency and voltage limits. If there is no control of voltage and frequency over that island portion, and if that is going to change drastically, then whatever equipment you have connected, there are fair chances of damage of those equipments. Is that clear, that thing?
Yes, sir.
Yes, sir.
Absolutely.
Yes, sir.
Yes, sir.
Okay. The second issue is related to the power quality, but anyway, we are not talking more about power quality because that is itself another area, right? So, but you assume, because I have already explained you that power quality is also another important issue. Personal safety is also an important issue, because see, whenever island is formed, what grid suppose you are working in grid in substation, what you will do, what is your first task? You have to send your lineman and see why that breaker has opened, why that fuse has opened, right? So on utility side it's fine, no problem, that breaker has opened, but that island is already working, right? The supply is available in that island portion. So whatever person utility is going to send for maintenance work, they may get in contact with the live part of the equipment in an islanded portion. So they may get an electric shock. So personal safety is also an important issue. That's why we need to detect the islanding term or islanding. Whenever it occurs, we need to detect it, right? So I think, Naman, may I stop here if any questions are there?
Hello.
Hello.
We can go for a break of 5 minutes if the participants want to ask something.
No, we have a time up to 11 o'clock, na?
Yes, sir.
Yes, sir.
Yes, sir.
So I think I stop here. If any questions are there, I am happy to answer,
Yes, please, participants.
because I have another meeting at 11 o'clock.
Sure,
So
sure, sir. No problem, sir. Please, participants, if you have any question, he has done extensive work in the protection area. Uh, Dr. Bhalja has done extensive work in the protection side of the power system. So he would be able to answer any of the queries related to the protection of the
Uh,
power system or microgrid.
good,
Yes, Jignesh.
good morning, sir. Good morning, Sobi, sir.
Good morning. Good morning.
Good morning, Bhavesh, sir.
good morning.
Uh,
Please tell.
Sir, I have one question which is not directly related to this topic. Just I want to know whatever you have knowledge on this particular problem. The problem is missing operation and sympathetic tripping of the of the relays of the power distribution system with the distributed energy resources. So what are the issues of this? What is the exact solution or remedies possible for this problem of the missing operation and separate tripping of the power distribution system relays?
So then, in that case, there is no exact solution existing, right? Maybe you have to search some papers for that. So you can use digital relays as one of the solution, but still digital relays have some uh, disadvantages also. Maybe exact solution is not available. Partial solution that is possible, right? And maybe with some you need to use some entirely different strategy, right? Other than conventional relays and like that, you may use IDs with communication facility, but those things are very costly, right?
Okay, sir.
Yeah.
Okay, sir. Thank you, sir, for the information and the answer to the question. Thank you, sir.
Anybody else?
Sir, there is one question in chat box asked by Swasti Krishna.
Okay.
Is
Let me
this
see.
is this Opel RT simulator is specific for RT Lab software only? Can I validate the result from OpenDSS software by using Opel RT?
That I don't know, huh? Because whether it is supported by some with some with whether it supports some other software, you need to ask the, or you need to see the Opel RT leaflet or maybe brochure, right? So that I am not aware for, because I don't know whether that is supported or not, because where I worked, we already have that software, so I just simply use it. Okay. And we are going to purchase OpenRT. I will definitely check whether the Open DSS is supported by OpenRT or not. But at present, I said I do not know about this.
Sir, if you won't mind, can you share some of the features? What can be done with the Opel RT, and what are the limitations, if you can, sir?
No. OpenRT is
As you have already worked on, so that may be useful for
no.
the.
So OpenRT, the features are, means whatever, you see, whatever software is there, that can be coordinated or correlated with MATLAB, right? So whatever it is similar to DSpace. Those you have used the DSpace, whatever you can do in MATLAB, you can directly bring it to the DSpace. So same thing is also possible in OpenRT also, right? The only thing is that because of the hardware in loop part, they are providing some specific controller or with some specific core. So that's why it is costly. Otherwise, the features are similar to this space. Only thing is that it is a hardware in loop simulation, where in this space hardware in loop simulation is not possible, right?
Yes, sir.
It is
Yes, sir.
only simulator.
Yes, sir.
Yeah.
Yes, participants, if you have any question, Naman, please.
Any question, participant? I think, sir, there is no questions.
Okay. Thank you. Thank you.
Bhavesh sir, I would like to thank on behalf of FDP and the Sarvajanik College of Engineering and Technology for such an interesting session. And we are very much thankful for you that you have spared some time from your busy schedule, and you have shared uh, some aspects from the protection which we have not yet discussed in so far in last 2 or 3 days of this particular FDP.
Yeah,
So it
but
would be.
first of all, I would say sorry because I forgot. Because the reason is that means I, though I have means put it in my calendar, but somehow I missed, because one NPTEL lecture I have to publish and finish before 31st December.
No, no,
So
sir, it's okay.
yeah, so the one course is going to live from January. It is on digital protection of power system.
Okay.
So that's why, because of that, I forgot. So I said sorry for that.
No, sir, we know that you have very busy and hectic schedule, and as you have at least spared some time for this, that we should be thankful and we should be grateful for you. So thank you very much, sir.
Yeah, thank you, thank you.
Thank you very much, sir.
So may I leave now, because I
Yes, sir.
have
Yes, sir. You
another.
may
Yeah,
please. You may
yeah.
please.
Okay, thank you. Bye.
Thank you.
Thank you, sir.
Yeah, bye, bye. Okay.
Now all the participants, the next session will start at 11:15. That will be conducted by Dr. Ashutosh Giri, and it would be on the role of intelligent techniques in microgrids. So we'll start the session at 11:15. Please be on time. And now there will be a break of around 20 minutes. So we'll start the session at 11:15. Thank you.